In the last video, I created 3 color threads, all tasked to run the countdown method on a single instance of a stopwatch. Initially, when the loop variable I was a local variable, the threads had no conflict with each other. They all successfully counted down from some initial starting point. When I used an instance field, however, for the loop variable, my concurrent application fell apart. On this slide, I'm showing you a conceptual picture of the countdown method simplified to show the for loop block. Specifically, I'm showing the for loop's initialization statement as well as the printf statement. Each box shown in this diagram is a unit of work, and you can see that units are logically nested one in another. Only the smallest blocks might be atomic. I'll come back to this term in a minute. Think about each of these blocks as having a door through which many threads can enter at any single time. There's no queue or line, so all threads can show up and enter at each of these boundaries at the exact same time. A thread can be halfway through the work in any one of these blocks when its time slice expires, and it then has to pause or suspend execution to allow other threads to wake up and execute. This means another active thread has an open door to that same unit of work where the paused thread is only partially done. When threads start and pause in the same blocks as other threads, this is called interleaving. As we saw in the last video, one result of interleaving is that a shared resources state may change while a thread is paused in the middle of its work. In this case, one thread interferes with the work of another. When multiple threads run concurrently, their instructions can overlap or interleave in time. This is because the execution of multiple threads happens in an arbitrary order. Remember, the order in which the threads execute their instructions can't be guaranteed. In programming, an atomic action is one that effectively happens all at once. An atomic action can't be stopped in the middle. It either happens completely or it doesn't happen at all. Additionally, side effects of an atomic action are never visible until the action completes. Even the simplest operations, like some decrements and increments, aren't atomic, nor are all primitive assignments. For example, long and double assignments may not be atomic in all JVMs. This slide shows 3 examples of operations that may not be atomic. In other words, even simple statements can translate to multiple non-atomic steps by the virtual machine, which opens the door to interleaving threads. Now that we know what interleaving is, how can we prevent it? Well, first, be very careful about shared objects. In the case of this code, it doesn't make any sense to have all threads sharing a single stopwatch instance. Imagine if a running thread had a different time unit, for example, or could change the time unit while running. A lot of things can go wrong if your threads are sharing objects not meant to be shared. To fix my code, I'm simply going to create 3 stopwatch instances. I'll first rename stopwatch to greenwatch. I'll copy this statement and paste it twice directly below this. I'll change the first copied variable to be purplewatch and the next one to be redwatch. Now, I've got compiler errors in each of my thread creation statements. I'll change stopwatch in each case to be the coloured coded watch that matches the thread name. I'll run this. This output looks a lot better. By giving each thread its own instance of stopwatch, I've almost ensured that I won't have trouble with interleaving threads. I say almost because I could have made that field, I, in this case, static. That would result in the same behaviour as if we were sharing stopwatch because a static variable is shared by all its instances. What if we had designed the stopwatch to be an immutable class by following the rules we learnt in an earlier section to do this? Certainly, the field I, if it were final, would never be used as a loop variable. Using immutable objects when dealing with concurrent threads simplifies techniques we might need to use otherwise and eliminates some bad programming practices. An immutable object is said to be thread safe for this reason. What does it mean to be thread safe? An object or a block of code is thread safe if it isn't compromised by the execution of concurrent threads. This means the correctness and consistency of the program's output or its visible state is unaffected by other threads. Atomic operations and immutable objects are examples of thread-safe code. In real life, there are shared resources which have to be available to multiple concurrent threads in near real time. For these, we'll need to control access to the resource to protect it from the effects of interleaving threads. You can think of some of these techniques as forcing threads to wait in line until one thread has finished a full unit of work and not just an atomic operation. Before we get into this, there's one more problem I wanted to demonstrate. It's similar to the problem we just saw, but it has nothing to do with atomic operations. For this, I'll create a new class called CacheData with a main method in my dev.lpa package. I'll set up a private Boolean field called flag and initialize it to false. Next, I'll have a method to toggle this flag. So flag will be set to not flag, getting the opposite value each time this method is called. I'll call my accessor method here, isReady, and that just returns the flag value. Next, in the main method, I'll create an instance of my class first. Now, I'll set up a thread that's responsible, after some kind of work, for setting this flag to true. I'll create a variable named writerThread and construct it from a lambda. I need a try catch because I'm going to call sleep. I'll sleep for 1 second and I'll use time unit here to do that. And I'll do the usual catch here. After sleeping for 1 second, which is just a placeholder right now for some kind of task that might need a little time, I'll toggle the flag so the object is in a ready state. I'll print out the value of the flag at this point. My second thread is another task that needs to wait until the first thread is ready. I'll call this one the reader thread. And while the ready flag is false, I'll just keep looping. Once the example instance is ready, I'll print my next statement. I'll start both threads here. Running this code, I see the first statement gets printed, indicating that my object's flag has been set to true. But notice that my code in the second thread, the reader thread, seems to be stuck in that loop. I'll stop execution manually. So what's happened here? This code is a demonstration of something called memory inconsistency. To optimize the performance of threads, the operating system may read from heap variables and make a copy of the value in each thread's own storage cache. In other words, each thread has its own small and fast memory storage that holds its own copy of a shared resource's value. This is a little bit different from the concept of the thread stack, which represents data visible only to its own operations. Because of this caching, one thread can modify a shared variable, but this change might not be immediately reflected or visible on the heap. Instead, it's first updated in the thread's local cache. When multiple threads are accessing the same data, it's possible for operations of one thread to not be visible to the other thread immediately. This is because the operating system may not flush or push the first thread's changes to the heap until the thread has finished executing. This is called memory inconsistency and leads to errors like we're seeing in this example. Looking at this code, let's talk about what's happening here. The writer thread sets the flag to true after a delay of 1 second using example.toggleFlag. Meanwhile, the reader thread is actively waiting in its busy wait loop. The reader thread's local cache isn't getting updated with the modified value of the flag variable after the writer thread toggled it. As a result, the reader thread is stuck in its loop indefinitely, waiting for the flag to become true, even though the writer thread has set it to true. To fix this situation, I can add one keyword, a modifier, to my flag's declaration statement. This modifier is volatile, and I'll add that before the return type and after the private modifier. Let's run the code now with this one change. Now, you can see both statements are printed and the application terminates naturally. What does this volatile keyword really mean? The volatile keyword is used as a modifier for class variables or fields, in other words. It's an indicator that this variable's value may be changed by multiple threads. This modifier ensures that the variable is always read from and written to the main memory rather than from any thread-specific caches. This provides memory consistency for this variable's value across threads. Volatile has limited usage though. It doesn't guarantee atomicity, so in the previous example, with our interleaving colorized threads, volatile wouldn't have helped. There are specific scenarios when you'll want to use volatile. The first is when a variable is used to track the state of a shared resource, such as a counter or a flag, or when a variable is used to communicate between threads. You should never use volatile when a variable is only used by a single thread, or when a variable is used to store a large amount of data. In the next video, I'll be talking about another way to ensure your code is thread safe. This is called synchronization, so let's move on to that topic next.